Hello, everybody. Let me introduce myself. I'm Mohammed Al-Jarrah, a PhD candidate at the University of Manchester. I'm going to present my article on the performance of Downlink NOMA systems over Hyper-Rayleigh feeding channels. My co-authors are Dr. Arafat Aldweik from Khalifa University and Dr. Ahmad Alsusa from the University of Manchester. Due to the increasing demands on network resources, NOMA is introduced to enhance the spectral efficiency of the network. In general, models like Nakagami and Rayleigh feeding channels assume very large number of reflectors. However, in areas like rural areas, the number of reflectors is usually limited, and thus Hyper-Rayleigh channel is better fits such channels. The typical system model of NOMA system in downlink scenario consists of a base station transmitting data traffics to two users using the same resource block. And to do so, the base station superimpose the signals of these users as shown in equation 1. And it's shown in equation 2 for a special case when two users are deployed. And usually one of these users is close to the base station, which applies SIG detection to decode its own signal, and the other user is far away from the base station. In Hyper-Rayleigh feeding channels, let's assume that we have a number of scatterers in the environment, then the received signal at the nth user can be displayed as this equation, which contains a sum of all reflected signals. And the figure here shows the Hyper-Rayleigh feeding channel, and it's compared to the Rayleigh channel. And it can be seen from this picture that for low number of reflectors, there's a big deviation between Hyper-Rayleigh feeding channel and the standard Rayleigh. And in order to simulate the NOMA system, we need to order the channels, and thus these two figures show the ordered channels, or the ordered Hyper-Rayleigh channels. At the receiver side, users need to implement the successive interference cancellation, or what's called SIC, in order to extract their own signals. The simulation parameters used in this paper are as follows. Monte Carlo simulation with 10⁷ realizations was used. Also, the base station and users use a single antenna, and the base station apply gray coding with QPSK constellation. The channel between the base station and each user is modeled as ordered Hyper-Rayleigh flat feeding channel with unit power, and the number of users is 2. And the power allocation coefficients are set to 0.7 and 0.3 unless it's specified otherwise. This figure shows the bit error rate of two users for different values of mixing coefficient A, and it also compares the performance of Hyper-Rayleigh channel with the standard Rayleigh channel. And as can be seen from this picture, there's a big difference between the bit error rate performance between Hyper-Rayleigh and the standard Rayleigh channel. And in this simulation, we consider the two-ray model, or Hyper-Rayleigh channel with number of scatterers equals 2. This figure shows the bit error rate for two-user NOMA system for different values of number of scatterers. and the results is also compared with the standard Rayleigh channel. And as can be seen from this picture, as the number of scatterers increase, the performance of Hyper-Rayleigh channel starts approaching the Rayleigh or the standard Rayleigh channel. This figure shows the bit error rate with different values of the power allocation coefficients, and it can be seen from this picture that if the power coefficients, or if the total power is equally divided into the two users, or if you use beta 1 equals beta 2 and equals 1/2, the performance of the system will be so bad. In conclusion, the bit error rate performance of Downlink NOMA was studied under Hyper-Rayleigh channel. Also, SIG-based detection was applied by users for efficient signal extraction. It has been shown that there's considerable difference in the bit error rate values when Hyper-Rayleigh channel is compared to the standard one. And it was also shown that the power allocation is very critical to provide users adequate quality of service in terms of the bit error rate. For future work may include the analysis of bit error rate for NOMA communication system under Hyper-Rayleigh fading channel. Also, the optimum power allocation for user equipments which guarantee the best quality of service for all users will be studied. And this is an acknowledgement for the supporters of this project, and thanks for your attention. For any question, you can contact me on this email address.